right, good morning. We're going to get started now. As you log in, remember to type your name and or alias and other information into the chat bar to get bonus points if you're in one of my classes. This is for Math for Liberal Arts, and we're looking at Chapter 11, Section 3. We're going to talk about conditional probability, which is exactly what it sounds like, finding the probability of an event under certain conditions that we have knowledge of. And then we're going to talk about when we see the word and in a problem, that corresponds to multiplying. And these two ideas are actually related. So let's start with conditional probability. Sometimes the probability of an event has to be computed using some knowledge that another event has happened or is happening or will happen. And this type of probability is called conditional probability. The probability of event B computed on the knowledge that event A has happened is called the conditional probability of B given A. Right, so we're saying what's the probability of B given that we know A has occurred, because sometimes knowing that another event has occurred changes the chances of B happening. The notation that we'll use is P parentheses B and then a bar and then A. So we read that probability of B given A. Okay, as an example, suppose that our sample space, my PowerPoint shut down and reopened. That's weird. Okay, so we have the numbers 2 through 9, and we're going to randomly select a single number. The events that we're interested in analyzing are A is the event that the selected number is odd, and B is the event that the selected number is a multiple of 3. And so let's start by answering part A. What's the probability of B? So the probability of B is referring to the probability that the selected number is a multiple of 3. So in our set, which numbers are multiples of 3? Let's see, 3, 6, and 9 are multiples of 3. And the probability definition tells us you just take the number of favorable outcomes divided by the total number of outcomes. So in this case, the number of favorable outcomes is 3. The 3, the 6, and the 9, so that's 3. Out of the total number of outcomes, which there are 8 of them, 2, 3, 4, 5, 6, 7, 8, and 9. So 3/8 is the probability with no other information of drawing a multiple of 3. Okay, part B asks us to find the probability of A and B happening. All right, so the probability of A and B, remember, and is intersection, it's the overlap. So for A, we're looking for the number to be odd, and for B, we're looking for a multiple of 3. So which of the multiples of 3 are also odd? Just the 3 and the 9. So for part B, we're looking for the probability of the 3 or the 9 being drawn. So that's going to be 2/8 or 1/4. Now part C is very different. So for part C, we're asked for the probability of B happening if we know that A has happened, something in A has happened. All right, so we know that an odd number has been selected. So either the 3, the 5, the 7, or the 9 has been selected. So what's the probability that it's a multiple of 3? Well, we can't use all the multiples of 3 because, or I should say, we're not interested in whether all the multiples of 3 have happened, because we know that only 3, 5, 7, or 9 has occurred. So we have to restrict ourselves to just those multiples of 3 that happen to be odd, right? Like we did a minute ago. 3, 9. But the difference here is that our universe of possibilities has shrunk, right? Our sample space has been adjusted or restricted because we know that the other members of the sample space, 2, 4, 6, and 8, did not happen. So when we're calculating our probability, we still have our number of favorable outcomes is 2, but we've restricted our total number of possible outcomes down to 4. So the probability that we get a 3 or a 9, given that we know we got a 3, 5, 7, or 9. So that means it's going to be 2 out of 4, or 1/2. So there's a much greater probability of getting a 3 or a 9 when you know that it's got to be an odd number than there was of getting a 3 or a 9 when we had to take the whole sample space into consideration. This slide's messy. Let me fix it. Okay, so let's talk about the formula for conditional probability of B given A. So the notation was P parenthesis B and then a line and then A. And so we have the probability of B given that A has occurred. Okay. And if you'll notice, since we know A has occurred, we can't consider anything outside of A. So we can only look at things inside A, but they also have to be, our favorable outcomes have to not only be in A and B. So what are we saying there? They're in the intersection of A and B. So when you're doing the probability, a conditional probability, you're actually going to find the favorable outcomes are in the intersection. So we're looking for the number of ways both A and B can occur. And then the sample has been restricted down to what we know has happened. So instead of being the number in the sample space S, we're just gonna have this new adjusted sample space that's just going to include the things in A. Okay, so we have the number that are in A and B divided by the number that are in A. Now, as usual with all of these formulas, if you take the n out and replace it with a p, so you're talking about the probability of A and B divided by the probability of A, you're still going to get the same number, because remember the only difference is that the denominator. We talked about that in class the last time. It's going to work out whether you have probability notation or counting methods notation. It'll work out the same. So let's look at an example. Given a family with 2 children, find the probability that both are boys, given that at least one is a boy. Okay, so when you're working a problem like this, it's important, really important, to identify the sample space. the original sample space. And then when you see the word given, that's an indication that we've restricted the sample space down to just part of it. Okay, so our sample space is the number, all the possible outcomes for having a girl and a boy. So we could have two girls, we could have a girl and then a boy, we could have a boy and then a girl, or we could have a boy and a boy. So if A is the event that we have at least one boy, you look for all the outcomes in the sample space where you see either one boy or two boys, and that would be at least one boy. B is, we're going to let be the event that we have two boys, which there's only one boy. So what we're trying to find is the probability that B happens, two boys, given that we know we had at least one. So what does that mean? Well, where is the overlap between A and B? Well, B is boy, which happens to be, in the set that's at least one boy. So A and B would be what these two have in common. Well, there's only one way that can happen, boy. How many are in A? Because we know we're not going to divide by 4 the total number in the sample space, because we know that at least one boy was born. We have that knowledge. So there's really only 3 ways, not 4, that can happen. So your probability is going to be 1 divided by 3. So again, take the number of ways that you have A intersect B divided by the number in A. Now, just to show you that this could work even if we use the probability version of the formula, what's the probability of getting boy out of the whole sample space? That would be 1/4, right? And the probability of A happening out of the whole sample space would be 3/4. 1/4 divided by 3/4, the 4's cancel out, right? You invert and multiply, if you recall. 1/4 divided by 3/4 turns into 1/4 times 4/3. You might have heard this as keep, change, flip. But in any case, when we multiply here, the 4's can be reduced, and we're left with just 1/3 again. So it's just going to depend on what information you're given, which version of the formula is helpful to you. But they both give you the same answer. Oh, another messy slide. Okay, let's look at this one. The table shows the results of a restaurant survey. I think we've got a couple problems in this section that use this survey. By the way, as I'm talking, if you have any questions, please feel free to type them into the chat bar. There's a little bit of a delay between when I speak and when you hear me, but just be patient and I'll answer your question. Also, if you could at some point before you log out, give a thumbs up to the video. That'll help other students to find the video. Okay, so let's look at this, my math lab problem. It says the table shows the result of a restaurant survey, and we see that people were interviewed during lunch and dinner, and they were asked if the service was good or the service was poor, and we have recorded the results here. We're asked to find the probability that the service was good given that the meal was lunch. Okay, so let me just go back. Okay, so remember, here's the formula. The probability of B, given that A has occurred, is the number of ways that A and B can occur divided by the number of ways A can occur. So let's write that down, or you can use the probability version of the formula. So let's go ahead and write that down. So the probability of B, given that A has occurred, is going to be the number of ways that A and B occur divided by the number of ways that A can occur. So in this case, when you see the word given, that's the bar in the notation. So we're trying to find the probability that the service was good, that's B, given that the meal was lunch, that would be your A there. Okay, so let's just make a note that this is our B, given that A has occurred. Okay, so first of all, just to make sure we're all understanding the chart, the number 23 here represents the lunch patrons who said that the service was good. So there were 23 of those. And the 25 represents the number of people at dinner that said that service was good. But we were given that the meal was a lunch. So essentially what's happening is we are restricting ourselves to just answering questions about lunch. We were given that it was lunch, so we don't have to worry about dinner. All right, so what's the probability that the service was good? Well, how many people said the service was good at lunchtime? 23. So the number in A intersect B, lunch and good service, would be 23. And out of the total number of people who had lunch, by the way, 23 plus 33 equals 56 is the total number of people who had lunch. So 23 over 56. All right. So the main idea here is, notice there were 48 people who had lunch altogether, but we restricted ourselves only to those, or let me say that a different way. I said it wrong. There were 48 people who had good service altogether, but we restricted ourselves to only those during the lunch service because we were told that the meal was lunch. So the number of favorable outcomes was reduced from 48 to 23 because of that. Also, the total number of outcomes would have been 97 normally. That's how many total people were surveyed. But since we're only concerned about lunch, that number was reduced to 56. So when you have a conditional probability, it's going to reduce both your favorable and sometimes both your favorable and your total number of outcomes, but definitely at least one of those. Okay, now here's an interesting definition. It says 2 events A and B are considered independent. By the way, people get this confused with mutually exclusive, so make sure you distinguish between those when you're studying for the test. 2 events are independent of each other if knowledge about the occurrence of one of them has no effect on the probability of the other. So for example, if we were to find the probability of B given that A has occurred, that would still be just a regular old probability of B. A didn't affect the probability of B happening, so they're independent. Probability of A given that B has occurred, same thing. Knowing that B happened doesn't affect the likelihood that A will happen. So this is the definition of independent events. So if you're asked to confirm if 2 events are independent, you would want to confirm that these equalities hold. So as an example, to check for independence, if we know a pair of dice are rolled, and one is red and one is green, and A is the event that the red die is odd, and B is the event that the green die is odd. Intuitively, you probably know that if you roll those 2 dice, the roll you get on one is completely independent of the roll that you get on the other one. But let's see if it fits our definition of independent events based on whether the probability of B is actually equal to the probability of B given that A has occurred. Okay, so remember what we're analyzing here. The odds, right? So A is the event that one die is odd, the red, and B is the event that the green die is odd. So let's take this one step at a time. All right, so find the probability of an odd green. All right, so we need to find the number of favorable outcomes, N of B, and the total number in the sample space. And what I'd like to do is remember, whenever we have a problem involving two dice, I recommend using the product table. So we're going to look at the product table and look for the probability of getting an odd green by counting the number of ways to get an odd green and then dividing by the total in the sample space. So here's our product table. All right, here's the green die. In order for the green die to be odd, it has to be a 1, a 3, or a 5. There are 6 ways to get a 1 on the green die, 6 ways to get a 3 on the green die, and 6 ways to get a 5 on the green die. So that means that there's a total of 18 ways to get an odd number on the green die out of the 36 possible outcomes. So the number in the sample space is everything in the chart. That's 36. And the number of ways to get an odd on a green die is 18. So if you divide that, the probability of getting odd on a green die is 1/2, which makes sense, right? Half of the values are odd and half are even. All right, now let's find the probability of B given that A has occurred. So we're going to find the probability of getting an odd green given that the red die was odd. Okay, so once again, we are going to have to find, according to the definition of conditional probability, the number that are in A and B, and divide that by the total number in A, because that's our restricted sample space. So I'm going to go to the product table now, and we're looking for odd greens and odd reds, right? Oops, let's go back. Okay. So I'm going to erase this. Okay, so first of all, we are given that there's an odd on the red, which means we can completely disregard anything else. So we do not care about any of this. 6 is even on the red. Here, 4 is even on the red. That didn't happen. So we're going to restrict our table to just those situations where the red die is odd. Now, out of those that remain, in how many of them would the green die be odd as well? Well, remember, for the green die to be odd, we're looking in the 1, the 3, and the 5 column. So that would be whatever's left in these columns. Okay, so the number that are in A, the number of ways to have a red die that's odd, there was 6, 6, and 6 is 18. But out of those, how many were both a red die odd and a green die odd? So in this case, those are just the 9 that I put squares around. All right, so to return, the number in A is 18, and the number in A and B is 9. So what's the probability then? Well, we're going to divide the number of ways A and B can happen by the number in A. So that's going to be 9 out of 18, or 1/2. All right, so now we're asked to determine based on this whether events A and B are independent. So independent means that the knowledge that A occurred did not change the probability, and you'll see that is true. In each case, we got a probability of 1/2. Whether or not we knew that and the red die was odd did not have any effect on the probability that the green die was odd. So that means that yes, we have independent events. Now, technically, it's possible for the probability of A given B to be different than the probability of B given A, and you should check both, but for the sake of time, we're just going to check the one. Okay, let's look at a different example of checking for independence. A single card is to be drawn from a standard 52 card deck. A is the event that the selected card is an ace, and B is the event that the selected card is red. Okay, so do you think that these are independent events? The probability of selecting a red card and the probability of selecting a red card given that the card was an ace. So to me, when I first looked at this problem, it doesn't seem like these are independent events. It seems like one would affect the other, right? Because you're restricting the number of cards. But let's see if it is or not. The only way to know is to actually calculate the probabilities. So how many cards are aces? Well, let's go ahead and move to this page. No. Let's stay on this page. I like it better. Okay, so how many cards in a deck of 52 are aces? So you might remember that each face value, there are 4 cards with that value. So there's going to be 4 aces. Okay, how many red cards are there in the deck? There are 26 red cards. Okay, and what's the overlap? In other words, how many red aces are there? Because that's always going to be important. So the red aces are the ace of hearts and the ace of diamonds. So there are 2 of them. All right, so let's go ahead and find the probabilities here. So what's the probability of B? Well, it's the number of ways that B can occur, which is the number of red cards, divided by the total number in the sample space S, which is 52, right? So there were 26 red cards out of the total 52, and that reduces to 1/2, by the way. And now we're going to find the probability of B given that A has occurred. This is going to be the number of things, number of events in the both A and B divided by the number in A. In other words, the number of red aces divided by the number of I got myself confused for a second. Sorry about that. The number of red aces divided by the number of aces. Okay, so we said there are 2 aces that are red out of 4 altogether. So that's 1/2 as well. So in fact, knowing that the card was an ace did not affect or change the likelihood of drawing a red card, because either way, half of them were red. So we would say that these events are independent. Again, technically, you should also check the probability of A given that B has occurred, but we're going to skip that part. Okay. All right, let's go back to the lunch example. So in this example, again, we have this table that tells us the results of a survey. This time we're asked to find the probability that service was good. Oh wait, we already did this one, didn't we? Why do I want to do this one? Oh, okay. We found the probability that service was good given that the meal was lunch. And now let's ask ourselves, are the events of good service and a lunch meal independent events? Okay, so they will be independent if knowledge that the lunch meal occurred did not change the probability of service being good. So what we found was the probability of good service given that the meal was lunch was 23/56. So let's compare that to just the flat out probability that the service was good. Probability that the service was good is going to be the total number of people who said service was good out of the total number who took the survey. And we're not excluding dinner this time. So that would be 48/97, which is not equal to 23/56. If you wanted to check this, you can either confirm that they're both reduced to lowest terms. They can't be reduced any further, so they must not be the same. Or you can divide 48/97 and 23/56 and see that you don't get the same decimal. So no, these are not independent events. All right, now we're going to move on to events involving and. And this is related to conditional probability because, remember, the word and is intersection. And the conditional probability formula had the probability of A and B in it. So remember, probability of B given that A had occurred is the probability of A and B divided by the probability of A. So we can rearrange that equation by multiplying both sides by the probability of A, and we actually get a formula for the probability of A and B. The probability of A and B occurring is the probability of A times the probability of B given A. Now you might remember that we've said over and over again that when you see the word not, it involves subtraction. When you see the word or, it involves addition. And when you see the word and, it involves multiplication. And you see the multiplication coming up right here. Now, if A and B happen to be independent, realize that this probability of B given that A has occurred would just be the probability of B. So you would just be multiplying the probability of A times the probability of B if the two events are independent. So really, you are just multiplying. But if the probabilities are affected one by the other happening, then you have to take that into consideration. So if they're not independent, you have to multiply probability of A times probability of B with the knowledge that A has occurred. This sounds tricky, but it's really not as bad as it seems. And we'll go over some examples that you'll see how it kind of flows naturally. All right, so again, independent events, the probability of one event and the other both happening can be found by multiplying the probabilities of each of them happening. If you have dependent events, then you have to multiply the probability of one by the probability of the other given that the first has occurred. Oops, another messy slide. I need to clean these up. Okay, so here we have a bowl full or a jar full of balls of different colors, and it says Jeff draws balls from the jar below. He draws 2 balls. without replacement. Find the probability that he gets a red and then a blue ball in that order. All right, so we want to know the probability that he gets a red and a blue ball in that order. And why is it significant that it says without replacement? Hi, Tanya. Can anyone tell me why it's significant when we say without replacement? So he's going to draw a ball. He's not going to be putting it back in, and then he's going to draw again. That's right. So it's going to affect the number of possible outcomes. Will be one less on the second draw, right? Okay. So this is how we would work the problem. First of all, without replacement always means dependent events. What does that mean? That means the knowledge that one has occurred will always affect the probability of the other occurring because you've reduced the size of the sample space. And that's right, it'll be no repetition 2. We're not going to get the same ball twice. So let's count how many of each color we have. We have 4 red, 3 blue, and 2 yellow. Now what we're looking for, this is my notation for R1 means we drew a red ball on the first draw, and B2 means we drew a blue ball on the second draw. Now according to the formula we just saw, you multiply the probability of R1, red on the first draw, times the probability of getting a blue ball on the second draw, given that we know the first one was red. All right, so the probability of drawing a red on the first draw is going to be, we have 4 reds out of a total of 9 balls altogether. So that's where we get the 4/9 from. But once you've drawn that red ball, then how many blue balls are there and how many balls are left total? There are 1, 2, 3 blues out of 8 altogether. So that's where the 3/8 comes from. And we need to multiply because it's an and. So we're going to have multiplying, you can either multiply straight across and get 12 over 72 and then reduce, or another way would be to reduce 3 goes into 3 once, 3 goes into 9 3 times, 4 goes into 4 once, 4 goes into 8 twice, multiply straight across then, and you'll skip directly to the 1/6, which is approximately 0.1667. Okay, so that's an example of an AND problem. So whenever you're doing an AND problem, you multiply, but you have to take into consideration that the first thing has already occurred. All right, let's consider if we change this to with replacement. Okay, so it says Jeff draws balls from the jar below. He draws 2 balls, this time with replacement. So he's going to take one out and he's going to put it back. Find the probability that he gets a red and then a blue ball in that order. So because the ball is replaced, repetitions are allowed. So that means event B2, drawing a blue on the second draw, is independent of R1. The probability of one will not affect the other. So whenever you see with replacement, you know these are independent events and you won't have to worry about the probability of one given that the other has occurred. You can just multiply each probability. So again, we have 4 red, 3 blue, 2 yellow. The probability of red on the first draw and blue on the second draw is just the probability of drawing a red on the first draw and the probability of drawing a blue. You don't have to say given that red has occurred. You could, but it's not going to affect anything. So we're just going to multiply 4/9, the number of reds, divided by the total number of balls, 9, times, in this case, not 3/8, but 3/9, because all the balls are back in there. They've been replaced. So that means that we can multiply straight across, get 12/81, which reduces, if you divide each part by 3, to 4/27, or 0.148. Notice that there's a slightly smaller chance now because we put that one red ball back in, so there's a slightly less of a chance of getting a blue on the second draw. Okay. Remember, you can ask questions if you have any. The next item I want to look at says a pet store has 14 puppies, including 5 poodles, 5 terriers, and 4 retrievers. If Rebecca and Aaron, in that order, each select one puppy at random with replacement, that means they may both select the same one, find the probability that Rebecca selects a terrier and Aaron selects a retriever. Okay, so in this case, with replacement means these are independent events. So you can just find the probabilities of each and multiply them together. And still means multiply. Okay, because there is a replacement, the events are independent. So we're going to find the probability that Rebecca selects a terrier. Well, there are 5 terriers out of the 14 puppies. So 5/14 is that probability. Then we're going to find the probability that Aaron selects a retriever. Well, that's going to be 4 out of 14, which reduces to 2/7. And then we're going to multiply 5/14 times 2/7. The order doesn't matter. And you're going to get 10/98, which if you divide both those by 2, you get 5/49. So the probability that Rebecca selects a terrier and Aaron selects a retriever is 5/49. Okay, the most important concepts here are number 1, and means multiply, and number 2, with replacement means independent events. Okay, this example I really like because it combines some concepts that we've learned, so it makes it a little bit tricky, but I think once you see it, you'll understand. It says, if it snows tomorrow, the probability is 0.5 that John will practice his trumpet. If it does not snow tomorrow, there is only a 0.4 chance that John will practice. Suppose that the chance of snow tomorrow is 60%. What's the probability that John will practice his trumpet? So what's interesting about this problem is we have to consider different cases because we have the extra variable of snow or not snow, right? So the probability will depend on whether there's snow or not, but we know the probability of snow as well. So when you see the word or there, remember or means add, probability of this or that. Another way of saying that is we have 2 cases and we have to add the probabilities of the 2 cases. So, oops. Okay, so what we want, you always need to, when you're working a word problem like this, we need to organize our thoughts, right? So what we want is we want to know the probability that either it snows and John practices, or there's no snow and John practices, because either of those cases the result is that John practices, and that's what we want to figure out the probability of. So either it snows and John practices, or no snow and John practices. So the or means add. But the and means multiply. And we have two of those. So what we're going to do is we're going to use multiplication to find the probability that it snows and John practices. And we're going to use multiplication to find the probability of no snow and John practicing. But then we're going to add together the two probabilities to get the total probability. Now, in order to find the probability that it snows and John practices, we're going to have to multiply the probability of snow times the probability that John practices given that snow has happened. So we're going to need the probability of snow and the probability of practicing given snow. And in order to find the probability of no snow and John practicing, again, we're going to need the probability of no snow multiplied by the probability that he practices given that no snow has occurred. Okay, so what's the probability that he will practice given no snow, or given snow has occurred, rather? So let's go back to I don't like all that stuff being in there. Going back to the description of the problem, it tells us flat out that the probability is 0.5 that John will practice his trumpet if it snows, and it's only 0.4 if it doesn't snow. So if it snows, 0.5. If it doesn't snow, 0.4. We're also told that the chance of snow is 60%. So the probability that it will snow is 0.60, or just 0.6. So how would you find the probability of no snow? So that's a complement, isn't it? So remember, the probability of something happening is 1 minus the probability that it doesn't, and vice versa. They have to add up to 1. So this is going to be 1 minus 0.6 is 0.4. Okay, so we have the 4 pieces that we need to do the calculation that we want. Remember, the probability of snow and John practicing would be the probability of snow, which is 0.6, times the probability of snow, probability that he practices given that snow has occurred, which would be the 0.5. Or means plus. Now the probability of no snow would be 0.4 times practicing given no snow is also 0.4. So that means that we have 0.3 plus 0.16, which turns out to be 0.46. 0.46 is the probability that he's going to practice. So that's all summarized here on this slide. So this is a pretty complicated problem, but I hope it helps to illustrate that the or is add, and that the and is multiply, and that when you have an and, you have to take into consideration that the first thing has occurred. So you have to use the probability of B given A. Okay, that's where we're going to stop today. If you have any questions, please feel free to send them to me via email or to Skype me. The instructions, oh, I see a question. Sorry, Alexandra. Where did the 0.6 come from? So 0.6 came, good question. 0.6 came from the 60 per, went too far back. Hold on. The 60% chance of snow. So 60%, remember percent means per 100. So that's 60 over 100 or 0.60. So the chance of snow is 60% means the probability of snow is 0.6. Hi, Tanya. I know there was a typo in the syllabus that had the wrong time, and I do apologize for that. Okay, anything else? All right, so I'm going to stop there. Keep working on your My Math Lab. I did post an opportunity to retake the midterm, by the way. Some students told me that when they went in to take their midterm that the ebook was not working for them, but they didn't realize it was supposed to be. So I opened up the midterm for a second attempt. I will warn you that although I have contacted the testing center and made them aware of the problem, I'm not sure what they're going to do about it. So if you go in and take the midterm again, it would probably be a good idea to sit down at the computer, and before you start on the actual test, go ahead and try and open up one of your homework questions. See if you can get the ebook to open. If the ebook won't open, if it says something like you need Adobe Flash, then request to be moved to a different table. If the attending proctor is not willing to help you with that, you don't even have to bother taking the test at that time. Just go ahead and Skype me and let me know